All right, it's 8:30, so let's get started today. All right, good morning, everybody. How's everybody doing today? Halfway through our first week of school. I know this is an early class, so it's takes some adjusting to get used to waking up. But thank you, everyone, for coming today. So today, what my plan was is to basically just continue just with an introduction of fluids. So still some relatively, chill stuff today. And then next week, we're going to start with hydrostatics. So, on Monday, it was a little bit of a strange setup just because I had the slides. But this is kind of like more kind of normal what the lectures are going to be like. So you can see, if you look at the participants list, you'll see that I'm connected with both my laptop and my iPad. And I'll be writing on my iPad as if it were like a whiteboard. So, I'm a really big fan of whiteboard lecturing, which is, what I would normally do in person. So this is kind of the best emulation of that. Okay? So you can see here we have our learning objectives. So these are, we talked about these last time. And so the idea with these is that this is kind of like, it serves a couple purposes. So one, this is kind of like a little bit of an outline of what we're going to cover today. But also, these are kind of a good check of your information that, you can come back to these after the lecture and say, can I do these 4 tasks, right? You can kind of think of these as kind of like tasks that you can do. And if you can do them, great, then you got everything out of the lecture that I wanted you to get. But if not, then, you might want to maybe watch the lecture again or go through the notes. Okay? Are there any questions about the class before we get started today? Okay, so let's go ahead and get started. Okay, so we're still, in the first week, so we can still kind of consider this as like an introduction to fluids. So last time we kind of gave, we went over 2 definitions of fluids. So the first one being, the Wikipedia definition, which was, a fluid will constantly deform under an applied shear stress. And so another way that we can say this, and we can kind of relate it to the molecular structure of fluids, is that it doesn't really hold, it never really holds a constant shape, right? So let's compare. So let's say that you have a rock, okay? And then you also have a water balloon, okay? So the rock, is unequivocally a solid object, right? And so if you take your rock and you try to kind of squeeze it with your hands or you try to twist it and stuff like that, unless you're the Hulk, you're not really going to be doing much to that rock. That rock's just going to be just kind of itself, right? You might be able to move it a little bit, but the amount of deformation that you get is just a modest amount of displacement. So you might be able to kind of squeeze it a little bit, depending on how strong your hands are, right? But for the water balloon, the more you squeeze it, like the more pressure you add to it, it's going to keep deforming and deforming until you squeeze it and eventually it bursts, right? And as you're squeezing it, it's undergoing large deformation. So you can see that it's, not really holding the same shape. So that's kind of just kind of a visual, well, as best as I can, visual representation for kind of the difference between a solid and a fluid. Okay? So if you look at their molecular structure, that you can kind of see what this is. So you might have gone over this in maybe like a chemistry class or an 8th grade science class. So maybe this seems familiar, but basically what I'm going to do is I'm going to draw the molecules as little circles. I see the question in the chat, but I'll address it in a second. So if you remember from like maybe 8th grade science class or like your chemistry classes, the molecules in a solid are very tightly packed and they're very organized, right? So they look kind of like little soldiers in a row. And that's what gives it its rigid structure. Draw one more row. Whereas for fluids, the molecules, they might be packed together. They're a lot more free. So the molecules are much more free to move past each other. So that's what kind of gives it its behavior. Oh, is there a tapping noise that people are hearing?
Yeah, I could hear a tapping noise right now.
Okay, I think that's probably my me tapping on my iPad. Let me see. My mic should be off here.
It's not that bad.
Okay. Well, if it gets distracting, definitely let me know, and then maybe I'll move my iPad further away from my laptop. Okay. So I'm going to answer a question. So there's a question in the chat. So why do I say shear stress and not just stress? So that's a really good question. So when we're talking about fluids, a lot of times we talk about shear stress because that's what actually puts the fluids molecules in motion relative to each other. So by shear stress, what I mean is if you have kind of a block of fluid that looks like this, right? Shear stress would look something like this, where we would take the fluid and then we would kind of shear it just like this. Okay. And what's unique about this kind of stress is that it puts the molecules in motion relative to each other. Okay. So if I draw a couple layers here, so when this is exposed to shear stress, what's going to happen is that this top layer will move to the right, and this bottom layer will move to the left. So because you have this relative motion of molecules, you have something like this situation right here, where that's what's going to cause it to flow. So that's as opposed to a normal stress, which might act on the side of this thing right here. Okay. The thing with the normal stress is that it'll cause all the molecules to move together. So in that sense, you don't really have flow, which is, flow, you need to have kind of that relative motion in between the molecules in order to do that. So that's why we specifically say shear stress. So usually it's not that hard to generate shear stress. So if you think of, flow in a pipe, what happens there is that, your wall is always going to be solid. Right? So as you apply a pressure towards that, there's going to be a shear stress at the wall because the fluid has to stick to the wall because fluids adhere to solid surfaces, and that naturally generates a shear stress. So for a lot of times, especially if you have a solid surface, it's not hard to generate a shear stress, but that's generally what we say causes the motion. So there's a question of what does it say after molecules? It says sorry. Great questions, guys. Are there any other questions on this before we move on? Okay, so let's go ahead and move on. Right. So notice how I said on this slide, I made the distinction between solids and fluids, but if you kind of remember from your previous science classes, there's 3 states of matter, right? We have solids, we have liquids, and we have gases. Okay? So, why have I been using the term fluids all this time? So the thing with fluids is that, we went over this a little bit on Monday, is that both gases and liquids are considered fluids. if you think about it, both a liquid and a gas, if you expose it to, some shear stress, we expect both of them to flow, right? Obviously, liquids and gases are different from each other, but for most of this class, we can consider them the same. So you'll see me use examples that do like water. Water is probably the most common liquid out there, or fluid that we're going to use. We're going to use air quite a bit. So there's definitely differences in how they behave. But for most of this class, maybe up until we get to the last week of class, we're going to consider them, the same fluids. So, they're going to have different densities and different viscosities, of course. But just in terms of, the equations that we use, we're going to apply the same equations to both liquids and gases because we're going to consider them both fluids. Okay? And in a lot of situations, that's actually a very reasonable assumption to basically assume that they're the same and they follow the same equations. It's only once you get into like really niche situations like supersonic flow or really fast flow over an airplane that things start to get a little bit weird. Okay. All right, so let's talk about dimensions and units. So hopefully all of you have seen dimensions and units before. Maybe not defined in this way, but just like any of the physical sciences for fluids, are the dimensions for all of our quantities and our equations, and the units which we use to describe them are something that's going to be really important. Okay. All right. So first, let's throw some definitions. So let's first define dimensions. Okay. So dimensions are the physical measures by which variables are expressed. Okay. So some examples of this would be like mass, length, time, and we won't use it too much in this class, but another dimension would be temperature. You can kind of think of dimensions as kind of like the primary colors of science, right? So there's a lot of really complex units. Like for pressure, we have the units like for pascals, but you can build those complex units from these basic building blocks here. So mass, length, time, and temperature are kind of your basic building blocks for all the physical dimensions. Okay, so that's dimensions. Let's talk units. So units are simply just the names that we give to certain dimensions under certain systems. Okay. So some examples that you probably are familiar with, we have the kg or the kilogram. So this is a unit of mass. We have the meter, which is a unit of length. So units are just the names that we give. And as you guys are probably aware, there's lots of different systems of units. So here I've used two examples from the SI system of units, which is usually kind of the more convenient one to work with. But there's also the imperial system of units. There's the English system. There's lots of different systems of units out there. So when you're doing problems, especially the ones that involve numbers, you want to make sure that you're working in the right unit system, such that all your numbers will match up. Okay. Okay. Any questions on this before I turn the page? Okay. Okay, so in the notes, what I have is a big table, a big table that shows basically all the, a bunch of important physical quantities for fluids and their respective dimensions and an example of their unit. So I'm not going to reproduce that whole table here, but I will give you some important ones. Okay? So let's start with something simple. So the quantity I want to talk about first is area. Okay. Okay. So the dimensions for area would be length squared, right? Because in order to get area, you have to multiply a length by a length, essentially, right? I mean, there's different formulas, like there's a formula for a circle, but the dimensions are always going to be some kind of length squared. And then one example for a unit, so let's say, we do an SI unit, you would have meter squared. So that might be, one that you've used quite often, but say if we want to do an example in the imperial system, we would have like feet squared. Okay? That works as well. So both of those are valid units, but when you're doing complex problems, you want to make sure that everything's in the same units. But both of those are valid units because they have the same, they follow the same dimensions of this quantity, right? Okay, so let's do one that's a little more complicated. Okay, so let's do density. So density, remember, has the units kilogram per meter cubed because it's a mass over a volume, right? So the way that we express that with dimensions will be ml minus 3. Okay. So to express the fact that the length is in the denominator, I raise it to a negative exponent so that it goes into the denominator down there. Okay. Right. And so let's do pressure. Pressure is an important one, especially starting next week. Okay. So pressure, probably as everyone knows, is a force divided by an area. Okay. And so actually, what you can do sometimes is that, and you'll see this in the lecture notes, that instead of mass, force is sometimes used as the dimension that covers that. So actually, this pressure is actually more easily expressed in terms of force instead of mass. Right? So the dimensions that would be F, L minus 2. Okay? And we'll do a note. Sometimes force, more convenient than mass. Okay. And then an example unit for pressure would be pascals. That's the SI unit. And then the way you get pascals is you Newton per meter squared. Okay. All right, let's do one more, just because it would be important. So let's do velocity. Okay. So velocity is pretty simple. It's just a length over time. Okay. The way we express that in dimensions is LT to the minus 1. Okay. And then the units for that in SI units will be meters per second. So here I've just done 4 examples of some of the more common ones that we'll see in this class, but there's a table in the lecture notes that's really comprehensive, and it shows you both the versions with mass and the version with force. So definitely check that out as we go through the class. Okay? Are there any questions on this before we move on? Has the tapping gotten better at least? That's good. Okay. Oh, Yes, so the M is right next to density. So the M stands for mass. Right. Yeah. Mm-hmm. Okay. Oh, what am I doing? Okay, so next I want to talk about the concept of dimensional homogeneity. Oops. Okay. And so the idea with dimensional homogeneity is that, if you're, dealing with a certain kind of equation in fluid mechanics, every single term in that equation has to have the same dimensions. Okay, so let's write that down. Okay. And so the reason for this is that, with equations, we're always adding and subtracting different things. So whenever we add and subtract different things, they always have to be the same. They always have to have the same dimensions, right? So, if we go back to the previous page, it doesn't make sense if we have an equation where we take a density and we add it to a pressure. Like that physically just doesn't make any sense at all. So, it's always good. It's, whenever you're presented with a new equation, it's always good to check whether or not that equation is satisfies dimensional homogeneity. Okay, so let's do an example to kind of show you what I mean by this. Okay. So let's take a simple equation that you've probably seen from your physics classes. Right? So let's do the velocity of a rigid body. Okay. So I'm going to write it kind of big here just so that we can do our checks. Okay. So the velocity for a rigid body, v, is equal to its initial velocity. Okay. And a right here is our acceleration. Only one L. Okay. And then t here is time. Okay. And here we have our velocity. Okay. And so when I'm asking you guys to check dimensional homogeneity, what I want you to do is I want you to check the dimensions for every single term in this equation. Okay. So we have three different terms. Okay. So we have v, we have v naught, and then we have a times t. Okay. And so when I say term, I mean terms are basically separated by adds or subtracts. So this right here, this is not two terms, it's just one because they're multiplied by each other. So the different terms are separated either by pluses, minuses, or equal sign. Okay. Okay, so let's check the dimensions for this first guy right here. Okay. So this is just a straight up velocity, so that's easy to do. So the dimensions for this will be length over time, or LT minus 1. Okay. Okay. So this V naught right here is also a velocity, so the dimensions are going to be L over T. Okay. Okay. And then this last term right here, A times T, this is a multiplication term. So we have to multiply their dimensions by each other. Okay? So let's start with acceleration. So acceleration, we have L over T squared. Okay? And then the dimensions for time is just time, right? So if we perform this cancellation, so this T right here is going to cancel out with this exponent. So once we do that, then we have L over T. Okay? And so now that we've determined the dimensions for every term, we can see if they're homogeneous, right? So on our first term, we have L over T. On our second term, we have L over T. And on our last term, we have L over T. So all three of them match. So this equation is dimensionally homogeneous. Okay. All right, are there any questions on this example right here? I'll do another example after this just to kind of drive the point home.
You said that the last term is considered one term because it's multiplication.
That's right. Yes. Yeah, you'll see that more in the next example where I have a lot of multiplications. But when you multiply two things by each other, they're still kind of considered one term. So the terms are only separated by pluses, minuses, or equal sign.
Okay. Thanks.
Mm-hmm. Okay, so let's move on. Okay, so this formula is going to be a little bit more complicated. And it's actually from, much later in the course, actually. So this will be the equation that governs the settling of a spherical particle in a stagnant fluid. Okay? And if none of those words make sense, it's okay. We're only looking at just the dimensions of the equation right now. Later on, once we get to drag and lift, then we'll actually go over what this equation actually means. Although if you want a physical example of using this equation, if you remember from Monday, the video I showed you of the marbles dropping into the test tubes of liquid, this equation basically governs that behavior. Okay. Okay. So first we have the mass times the gravity minus pi over 8 times CD times rho times velocity squared. So this rho right here is density, and V is velocity, times the diameter of the particle squared is equal to mass times the acceleration. So the acceleration is dV dt. Okay. So there's a lot of terms here, so let's go ahead and define everything. Okay. So m will be the mass of the sphere. G is our acceleration due to gravity. Right. So pi and 8 are just numbers. So numbers don't actually have any units associated with them or any dimensions. They're just numbers. Okay. Next we have CD. So this right here is the drag coefficient. Okay. So whenever you see something that is called a coefficient, then they're not going to have any dimensions. So this is dimensionless. So it's basically the same as a number. Okay. Next we have rho, which looks like P. It'll be a constant struggle in this class determining whether I'm writing a P or a rho, but I'll try a bit harder this year. That was probably my #1 complaint last year. So rho right here is our density of the fluid. Okay. Next we have V. V is velocity. So D is diameter, okay? Right. Oh, so there's a question in the chat. So what is drag? So drag is basically kind of what you I think what most people call wind resistance. So if you stand in a in a river or something, or you stand outside on a windy day, you feel some kind of force that kind of pushes you in the direction of the wind. So that's basically the drag force right there. Yeah. So it's drag is a force, but the way that we often describe it is with the drag coefficient, which is dimensionless. So we'll go over this a lot more once we get to drag and lift near the end of the class. But I just wanted to look at this equation for now. Yeah. Mm-hmm. Okay. And even though this last term is a derivative, we can just state what it is. So this derivative, so this is dv, so it's derivative of velocity with respect to time. So all this is just acceleration. Okay. So we have a pretty complicated equation here with a lot of different terms. And what we want to do is we want to see if this equation is going to be dimensionally homogeneous. So ideally, every term should have the same dimensions. Okay? And so the way we're going to do this is we're going to take each term one by one, and we're going to write out the dimensions for it. And ideally, all three of these terms should match. Okay? So we'll call this y term 1, this big guy term 2, and then this guy will be term 3. Okay? So we'll go 1, 2, 3, and then we'll check their dimensions, and then ideally they should all match up. Okay? Any questions on just the setup of this example before we go about solving it? Okay. All right, so let's start with term 1. That one's actually pretty easy too. Okay, so our term 1 was mg. Okay, so we have a mass, and then we have multiplied by g. But g, remember, it's the acceleration due to gravity. Okay, so we have a mass times an acceleration. Okay. So let's write out the dimensions for each of those guys. So mass is just going to be m. Okay. And then acceleration is going to be L all over t squared. Okay. And so, nothing here is going to cancel out because everything's different. So then we have m times L all over t squared. Okay. So that's the dimensions of the first guy. Okay. So pretty straightforward. So this can happen sometimes when you don't have any cancellations, and that's totally fine. Okay, so let's do just because the second term is probably the most complicated. I'll save that one for last. So let's do the third term now. So we have m times dv dt, where we've established that dv dt is just an acceleration. Okay, so we have again mass times acceleration. Okay, so let's go ahead and write out the units for the dimensions for this. Okay, so we have mass is just m, and then acceleration is L all over t squared. Okay. And then this is exactly the same as 1, so we have m L over t squared. Okay. Okay. All right, so far so good, right? Which makes sense so far because we have two terms that are mass times acceleration. Okay. So now let's look at the second term. So this guy is kind of a doozy. So our second term is pi over 8 times CD, our drag coefficient, times density, times velocity squared, times diameter squared. Okay. Okay. So this guy's a bit of a doozy. Okay. All right, so the question, so how would we know whether mass m is for mass or m is for distance? So I usually use big M to do the dimensions for mass, And then I use little m to denote meters for distance. Yeah. Okay, so let's do this guy now. Okay, so you know, there's a lot of different variables here. So let's kind of go step by step. Okay. So you know, for these kind of dimensional homogeneity problems, I usually find that it's what simplifies my life quite a bit is to first get rid of everything that doesn't have dimensions. It's not like we're you know, killing them off. It's just, you know, we're kind of just hiding it from our view just so that they don't really confuse us in the end. Okay. Okay. And so we have a couple you know, variables here that are like that. Okay. So first we have pi over 8. So pi over 8 is just a number. So remember, numbers don't have any dimensions. So we can just kind of get rid of that guy. Not permanently, but you know, we're just gonna you know, not pretend it's not there. Okay. And we also have the drag coefficient. So remember, the drag coefficient doesn't have dimensions because it's just a coefficient. So let's go ahead and remove that guy. So now we're left with the density times the velocity squared times diameter squared. Okay. Are there any questions on this page before I turn it? Okay. All right, so then what we have left is density times velocity squared times diameter squared. Okay. All right, so what we're going to do is we're going to write out the dimensions for each of these variables and then cancel out what we can. Okay. Whoa. Okay, so let's start with the density. Okay. So the dimensions for density are going to be big M, mass, all over L cubed. Okay, so it's a mass over a volume. Okay. Next, we have the velocity squared. So that's going to be, velocity is going to be L over T. Okay. But since this velocity is squared, we have to square this entire quantity here. Okay, so we're going to distribute that exponent throughout. Okay, so we'll do that in the next step. And then last we have d squared. Okay. So d squared is going to be L. Okay. And then also we're going to square that guy too. Okay. Okay. So we've written out the dimensions for each of the variables in our term. Okay. So now let's distribute our exponents. Okay. So the density is not raised to any exponent, so we can just leave that guy alone. So we have m over L cubed. Okay. Our velocity is squared, so we're going to distribute that squared to every term. So we have L squared all over T squared. Okay. And then our diameter is squared as well, so we have L squared. Okay. Okay. So now we have to simplify this. So we need to cancel out some terms. Okay. So let's go ahead and perform the multiplications just so it's a little bit easier to do. Okay. So on top we have m times L squared times L squared. So that's going to be m times L to the fourth. Okay. And on the bottom we have L cubed times T squared. Okay. Right. So in that step, I just performed the multiplication. So I just did L squared times L squared, which is L to the fourth. Okay. Okay. So now we can simplify this. We see that we have L cubed on the bottom, and we have L to the fourth on the top. So three of the three L's on the bottom are going to cancel out with three L's on the top. Okay. So we have m times L to the first power, all over T squared. Okay. So that's the dimensions for that second kind of monster term. Okay. All right. Any questions on how we got this? Okay, so then now that we have the dimensions for all three terms in our equation, let's go ahead and check them. So for the second term, we have m times L over t squared. Okay, and if we compare that to terms 1 and 3, we also have m times L over t squared. So everyone is the same. Okay, so if all the terms in your equation have the same dimensions, then we can say that that equation is dimensionally homogeneous. Okay. All right. Any questions on this example before we move on to the next topic? Sure. Go ahead. Ask away. Right, so the question is, why is acceleration length over t squared? And so if you go to your kind of your usual units for acceleration, right? So acceleration, you know, let's take the SI units for acceleration. So acceleration has m over small m, so this is meters, meters per second squared. Okay, and so if we do the dimensions for this guy. So little m has dimensions of length, okay? And then s stands for seconds. So s squared is going to be big T squared. Yeah. Yeah, I think probably you guys are probably more used to thinking things in terms of units, because that's you know how you did your problem before. So you know if you're having trouble finding the dimensions for a certain quantity, think, you know, what are the standard units for this that I know for this guy, and then work out the dimensions from there. So that's usually a good way to do it. Question. So would volume be uppercase V and velocity in lowercase v? Typically, yes. Yeah, so volume typically does have an uppercase V and velocity does have a lowercase v. I did an uppercase V in this case for velocity, just because it was you know, we didn't have volume here. But in situations where you have volume and velocity in the same equation, that's usually the convention. So I'll use an uppercase V for volume and a lowercase v for velocity. Yeah, it's I think that's going to be one point of confusion for this class, is that it's you know, there's going to be a lot of variables, and a lot of them use the same symbols, unfortunately. So whenever we do come across that, I'll be sure to label everything, just so you guys know. I think, yeah, you know, the one I think is going to be most confusing is especially starting next week, is that we have pressure, which is given by a P for pressure, right? Okay, and then we have density, which is given by the Greek symbol rho. Okay, so they look very similar, and you know, here they might look different because I took my time to write them. But when I'm writing really fast, you know, these things can get confusing. So so the convention that I typically use is that when I'm doing P for pressure, I usually give the P a little ponytail like that. Okay, so if the P has a little ponytail, then you know it has pressure. But if there's no ponytail, then I mean density. But you know, I'll go over this a lot starting next week, because hydrostatics has a ton of pressure, density, and you know, they kind of get confusing. So, but that's generally the convention that I'll use. All right. Any more questions on this before we move on? Okay. So I want to talk. I want to kind of double back to something we did on Monday, which was fluid properties. So actually, in the notes, I have you know density, viscosity, compressibility, surface tension, and vapor pressure. But just kind of in the interest of time, I'm going to just kind of double down on density and viscosity, because those are going to be kind of the most important ones that we're going to need in this class. But if you're interested in learning about like vapor pressure, compressibility, or surface tension, which are kind of cool things, but they're not going to be really relevant for this class, and I'm not going to test you on it either. Then you can look in the notes. But I really wanted to make sure that we get density and viscosity down. Okay, so let's do density. Okay. So we talked about density on Monday as kind of something that characterizes the kind of the heaviness or the mass of a fluid. Okay. Oh, question. A property is a given dimension at any time. So a property does have dimensions. Yes. So each of the properties that you'll see here, they have their own physical dimensions and they have their own units. And it's always going to be the same. So density is always going to be a mass over a volume. Viscosity is a little bit more complicated, but it has its own dimensions as well. Yeah. Okay, so let's give a formal definition for density. So density characterizes the relative weight or relative mass of a fluid and is expressed as a mass per unit volume. Okay. So density is equal to rho, cursive P, is equal to the mass of a substance divided by the volume of substance. Okay. So we went over this on Monday. So this is kind of just a formal definition of it. Okay. And one thing that is useful to me is I like to always think of this as a ratio. Okay. Okay. So it's a ratio. Say you have a certain amount of liquid, right? It's going to be the ratio of how much that liquid, a certain amount of liquid weighs over how the volume of that liquid. So it's a ratio of how much mass there is per the amount of space that it takes up. Okay. All right. So one more piece of trivia is that the density usually is not constant for a fluid. So most of the time for our calculations, we assume that it is. But the density, just like any other property, as you might have learned in thermodynamics, is that your density is going to depend on pressure and temperature. Okay. So you have a glass of water, on your desk that might be room temperature. This has a certain density. But if you boil the water, so you basically raise its temperature by a large amount, then it's going to have a different density, right? So generally, what tends to happen for most fluids is that as the temperature goes up, the density goes down. Okay? And so we'll explore this a little bit. I think maybe in 2 weeks once we do buoyancy, because if you're familiar with hot air balloons, the way they work is that they heat up the air inside the balloon, right? And so when you do that, you make the air inside the balloon less dense than the air outside the balloon. And so that gives it kind of a net upward force that lets you kind of fly into the sky. Okay? All right, so the question is there a relationship between density and viscosity? So generally not. So there's you'll see fluids with you know, really high density and low viscosity, and you'll see fluids with really you know, high viscosity and low density. So a lot of that really depends on kind of the chemistry and kind of the molecular interactions in the fluid. So you know, there's fluids that are kind of all over the spectrum. So generally there's no relationship between the two. Yeah. They both do depend on temperature. So you know, if you heat up a fluid, you know, they're both the density and viscosity are going to change, but they're going to change in different ways depending on the fluid. Yeah, good question. Are there any questions on this before we move on? Okay. Okay, so let's see, where was I? Okay, so let's do another definition. So one definition that you'll see me use a lot in this class is that a fluid is incompressible. Okay. Okay. And so what incompressible means, basically, what that it's a word that means you can't compress it. Okay. But you know, for our calculation's sake, when I say a fluid is incompressible, all I mean is to say that the density is constant. Okay. And so, you know, this seems to contradict, you know, what I said, you know, just, you know, two minutes ago, that said, you know, density changes with temperature, right? And so when I say something's incompressible, how can density be constant when, you know, the density depends on temperature? So this incompressible assumption is an assumption. So, you know, a lot of times when we're doing calculations and we're doing problems, you know, we have to make some assumptions in order to make the problem, you know, easy enough for us to solve. So the incompressible assumption is one of those assumptions. So if you're reading a problem and you see, you know, the fluid is incompressible, you can say that, you know, whatever density that I give you in the problem is going to be constant. Okay. All right. So the comment: honey has a high viscosity and water has no viscosity. There were examples of those. Yes. Yeah. Great point. Great point. Mm-hmm. Yeah, so so the question was, can I give examples of fluids with high viscosity and low density, and vice versa? I can't think of any off the top of my head, but I can definitely look some up for next time. The thing is, like, there's so many different fluids, because, you know, we have gases and we have liquids and all that stuff too. There's some gases that are extremely heavy, but generally gases have pretty low viscosity. And then there's some liquids that, you know, behave the way that they do too. So that's definitely something I can look up for next time. Okay. So the question is, can we assume density is constant for all the problems we do? For, I would say, 90% of the problems that we do, you can assume density is constant. And I'll give it to you in the problem most of the time. If not, then it's something you're going to be solving for. So typically, you know, when density is not constant, those are going to be cases when we do compressible gas problems. And we're not going to do those until the very, very end of class. So 95% of problems, you know, up until the last, basically the last, you know, week or two of class, you can assume density is constant. And, you know, I'll give you plenty of warning, you know, before we get there. Okay. So let me give you some typical values of density. Okay. So we have water at 60 degrees Fahrenheit. Okay. So the density for this is roughly 999 kilograms per meter cubed. Okay. We have air. This is at room temp. So this is approximately 1.225 kilograms per meter cubed. Okay. So you can see there's a huge difference, which generally lines up with your intuition that water is a lot more dense than air. Okay. Okay, and then we have blood. Okay. So blood is slightly more dense than water. Okay? So you probably heard the phrase "blood is thicker than water." So we'll see that once we when we do viscosity. But at the very least, blood is denser than water. So you can start saying that phrase, and then people will look at you funny. But it's from here. Okay. Okay, and then just one more thing I wanted to review for density. So we have specific weight. Okay. So remember, specific weight is kind of like the relationship between force and mass. Okay. And so the symbol for specific weight is given by gamma. And the way that you do that, or the way that you compute it, is you take your density and you just multiply it by gravity. Okay. Okay. So instead of talking about mass, which is density, specific weight specifically deals with weight. So it's also a ratio. Okay. So you have the weight of the substance divided by the volume of substance. Okay. And the typical units for this would be, a force over a volume. So this would be like a Newton per meters cubed. That's the typical units for specific weight. Okay. All right. Any questions on this before we move on to viscosity?
I got a question. Will there be a point where we have to utilize the density value of blood?
Maybe. I mean, I just wanted to give you just some typical values here.
Oh, okay.
But there might be a problem later on where I ask you to use this. But this is just to give you put some numbers to that. Okay?
Yeah. Okay. Because I was curious, because I don't know if there might be a problem regarding the human body, and to hear that someone was having a temperature measure of 60 degrees Fahrenheit.
It is a little bit specific, but remember, density depends on temperature. So if you measured the density at like 100 degrees Fahrenheit, maybe someone's feeling feverish, then you're going to get a different density value.
All right. Okay. Making sure.
Mm-hmm. Yeah. So the question is there a specific value for room temp? There is, but this was the value that I just kind of looked up really quickly. But there's a different value for room temperature. It doesn't vary that much because liquids generally don't change density too much. Usually it's gases that have a much steeper density curve, but it does change a little bit. Yeah. Mm-hmm. All right. Any more questions on density? Okay. All right. So let's do viscosity. So while density, I feel like is pretty intuitive, and I think a little bit easier to define, viscosity is a little bit more difficult. Okay? So I think until we get to the part of the class where we do viscous flow, which is about halfway through, I'm going to mostly describe this in terms of just kind of a qualitative, kind of intuitive definition. Okay? So viscosity, you can kind of think of as it describes a fluid's resistance to flow. Okay. So fluids with high viscosity are much more difficult to get flowing than fluids with low viscosity. Okay. And so just to kind of give you a kind of a tactile kind of feeling towards this, fluids with high viscosity tend to feel stickier or feel thicker. So like if you ran your hand through like a tub of honey, right, it's going to feel really sticky and thick because, you know, it's going to be hard because, you know, the honey is basically resisting the motion of your hand through itself, right? And when you take your hand out, the honey really sticks to your skin, right? That's because honey is so viscous that, you know, it's resisting the flowing that's coming on, that's, you know, going off your hand. Whereas if you stick your hand in air, right, air has extremely low viscosity, right? You don't feel anything because, you know, there's hardly any air resistance, right? And you do like this, and then the air just kind of falls off your hand, just like that. Right? Yeah. So the question is, why do these fluids feel stickier? And you can think of it as the atoms. So like for highly viscous fluids, the atoms tend to or the molecules tend to want to kind of stay closer towards each other, and they don't flow as freely, right? So for fluids with lower viscosity than the molecules, they don't really care about each other, just like, you know, later, dude. But for like highly viscous fluids, then, you know, it takes a while because of, you know, those molecular forces, right? Right. Yeah. So there's a comment. London dispersion forces between atoms. Yep. That's definitely one thing that contributes. It's a lot of different factors, but that's definitely one big thing that contributes to it for sure. Okay. So we're running a little bit out of time, and there's one more thing I want to get to at the end because you need it for your homework. Okay. So I think I'll save most of the discussion for viscosity until you know, we get to that point. But let me give you some typical values. Right? Okay. So let's do our same three fluids. Let's do water, if I can count correctly, air, and blood, right? So now we can see if blood really is thicker than water, right? So all of these, I think, are going to be at room temperature, okay? So the viscosity of water is 8.9 times 10 to the minus 3 Pascal seconds. Okay. Air has a viscosity of 1.81 times 10 to the minus 5. Oh, I'm sorry, this is 10 to the minus 4 right here. I was looking at something else. Right. So water has a viscosity of 8.9 times 10 to the minus 4 Pascal seconds. Air has a viscosity of 1.81 times 10 to the minus 5 Pascal seconds. Okay. And then blood is 2.87 times 10 to the minus 3 Pascal seconds. Okay. So you can see here that, you know, air, which is a gas, has a very, very low viscosity, and then blood, right, does have a higher viscosity than water. So indeed, blood is thicker than water. Blood is also more dense than water. So you can kind of do both those things. Okay. Okay. Any questions on viscosity? Okay. So there's one more thing I want to go over today, and it's kind of a you know, I'd say this is kind of more of like a practical thing, which is, you know, what a lot of people do out in the field, and that's characterizing flow. Because as you'll see as we go through this class, you know, fluid flow is something that's really complex, right? You know, a lot of times it requires a solution of a differential equation, or, you know, requires a lot of lengthy calculations. But a lot of times, you know, if you're talking to like a colleague or, you know, a fellow engineer, and you just want to quickly say that, you know, I want to tell you about this flow that I saw, just for kind of work purposes, you're not going to go through a lengthy calculation to show them, right? So there's ways that that we can describe fluid flow that doesn't require all these lengthy calculations. Okay? And the way that we do this is that we we use some of its key properties. Okay? Okay. And the key word here is flow. So these are going to be fluids that are going to be moving. Okay. You know, when you have moving flow, you have some kind of a measure of speed. So the key properties that are used to describe these fluid flow situations are: one is the size. Okay. Two is the speed, and three is the pressure. Okay. Okay. And of course, you know, you would also describe, you know, the density and the viscosity of whatever fluid flow that you're describing. But you know, if you're going to be describing the flow, you know, in like the Hoover Dam versus the flow that's, you know, the flow of blood in your body, you know, those have very different sizes, right? The Hoover Dam is ginormous, and your blood vessels are really tiny. They have different speeds, so the fluids are going to be moving at different speeds, and they have different pressure values too. Okay, so let's go over each of these ones and what they actually mean. Okay? So let's start with size. So this is probably one of the biggest things, because, you know, if you go up to someone and say, you know, I have a fluid flow, that doesn't really tell you anything about it, right? So that could be flow in, you know, the Hoover Dam, or it could be flow of blood in your body, right? So the first thing you have to do is you have to kind of describe, you know, what are the size scales of the flow that you're considering. Okay? And so to help with this, you know, we use what's called a characteristic size. Okay? Okay. Or another word that's used to describe this is characteristic length. Okay? And so what this typically is that it's some length, or some either some length or some area that describes that kind of is the defining size scale for your flow. Okay? Okay. And so I'll give you a couple examples. Okay. Sometimes it can be hard to pick out just one size for your problem, because, you know, a lot of times you're working with complex geometries and it's hard to pick out just one size. Okay? But I'll give you a couple examples to kind of show you what I mean by this. So let's say that we have flow in a pipe, right? It could be, you know, a pipe that, you know, leads to your sink, or it could be a flow in like the Alaska pipeline, right? So this pipe has some diameter, okay? And so typically when you're talking about like a pipe flow, the diameter will be your characteristic size or your characteristic length. Okay? Okay. So let's do an example from aerodynamics. So let's say that we have flow of air over an airfoil. And so the length of that airfoil would be your characteristic length. So if you know, if your manager comes up to you and say like, tell me the characteristic length, which is, you know, he just wants one number, these would be that one number that characterizes that flow. Okay. And this is important because, you know, when you're describing things to, like, you know, your manager or your fellow engineers, you know, you want to describe things quickly, but, you know, with enough detail that, you know, they understand what you're talking about. So finding that characteristic size will be something that's really important. All right, any questions on this? Okay. All right, so now let's do speed. Okay. So just like how there's a characteristic size, there's also a characteristic velocity. Okay. And so this describes generally, you know, how fast the fluid is moving in your system. Okay. Right. So if you think about, you know, the water that comes out of your faucet, you know, that has a certain speed. But if you're going to compare that to, you know, the flow of air over a fighter jet, you know, those speeds are going to be very, very different. So being able to characterize that speed is something that's also really important for these fluid flow situations. Okay. And so this could either be like the absolute maximum velocity that you achieve in your geometry, or it can be like an average speed as well. So you know, it depends on you know, what your application is. Right? Okay. Okay. And then the last one is pressure. Okay. And so pressure, I'd say, is only really only a factor for internal flows, so flows that are completely encased. So you think of things like a pipe flow or something like that. Okay. Okay. But it can be important for external flows too. So actually, you know, the flow of air in the environment oftentimes is driven by pressure differences that occur in the environment too. So so pressure is, you know, something that's always important, but most of the time it's used to describe internal flows like pipe flows. Okay. And so, you know, pressure is really important because pressure, remember, is a force over an area. So a lot of times your pressure forces are going to be the ones that are driving your flow. Okay. So you can kind of think of this, you know, from a solid mechanics point of view, as this is kind of like your driving force. So, you know, whenever you have like you know, a dynamic system in motion, it's always good to know, you know, what's the force that's kind of driving this motion. So for fluids, kind of the equivalent of that is pressure. So it's always good to know, you know, how is your flow being driven. So like an example of this would be like the blood pressure that you have in your body, right? So that blood pressure that your heart, you know, is constantly doing, that's driving the flow of blood through your body. Okay. So if I asked you just to describe like what's the characteristic pressure for like blood flow, then you would tell me that it would be like the average blood pressure in a human. All right, so questions like, does that mean there is a more flow at the bottom of a dam? No. So one thing that, you know, we'll learn, you know, in a few weeks is that fluids conserve mass. So whenever you have a certain amount of fluid that's coming into a system, that exact same amount of fluid has to come out, given, you know, assuming that, you know, you're under steady conditions. If it's unsteady, then, you know, you can have more flow coming in and out, or, you know, vice versa. But, you know, we'll be mostly dealing with steady situations. So any fluid that comes in has to come out in the exact same amounts, just because, you know, we know mass can't be created or destroyed. All right, any final questions? All right, so that's all I got for you guys today. But, you know, before you guys go, you know, if you hadn't before, you know that I like to do my minute papers. Okay. And so this minute paper will take the form of a survey that's on the course website. So if you go to Canvas, you should now be able to see the minute paper. Okay. So this is an ungraded survey. It's totally anonymous, so I won't you know, I won't be grading this. You know, typically the way that I do this is that I give everyone a note card in the class and basically answer these questions. But since, I can't give you guys a note card, we're going to be doing this through Canvas. And so there are 3 questions. So the questions are, what did you think was the most important point? What was the muddiest or the most confusing point? And any feedback that you have for the class that can help me improve, this virtual experience. So, it's not required. So, I mean, you don't have to do this, but, anything that you guys can give me from this will help me improve the class. And I think this, the first 2 questions are really important because it helps me gauge, if you guys got the most important points, and just anything that you guys are confused about, I can double back and kind of go over that again the next week. Okay? So I know this week was a little bit weird just because we had the course introduction, but anything that you guys write will be valuable. Okay. All right. So that's all I got for this week. So hope everyone has a great weekend, and I'll see you guys on Monday.
All right. Thanks again, Professor.
Yeah. Thanks, everybody. All right, so the question is, do we have homework for this week other than the intro email? So no, the only thing that's due this week is just the intro email. I'll probably post the homework assignment, the first homework assignment due next week on Canvas, probably later today. Yeah. Yeah, and I'll send an announcement for that too. All right, so the question is, the book states real fluids always stick to solid boundaries that contain them. So something like sand wouldn't be a real fluid. Sand is a very interesting thing actually, because it does exhibit a lot of fluid-like properties, but it's still technically a what do they call it? It has a different term, but sand does typically stick. It's just it only sticks in like a very small layer. So and it's true. That's true for fluids too. So like if you kind of pour out from a water bottle, the water actually is sticking to like the sides of the water bottle, but it's only sticking in like a very thin layer, and all the other fluids that are next to it are going, right? That's why we talked about kind of the shear stress and like the relative motion between particles earlier, because even though the fluid's sticking at the solid boundaries, there's shear stresses that are causing those molecules to have kind of relative motion from each other. So sand, I think, is kind of the same way. Although I'm not a huge expert in sand, but sand is weird. Sand is kind of its own thing. Although a lot of times it does behave like a fluid. Yep. All right, any more questions, guys? If not, I need to go pee really bad. All right, so if you guys have any more questions, you can definitely send me an email. And if not, I'll see you guys next week.